yeah, in this talk, we kind of bring a new paradigm where you can do a better concurrent execution for firmware, especially on those deeply embedded devices. So this is joint work between our colleagues from Northeastern, our advisors, and Meng from University of Waterloo. So first of all, I think there's no denying the fact that embedded systems and firmware are prevalent and very important in our daily lives. So the backbone of them are those tiny little MCUs. So contrary to what we have in personal computers and servers, which are designed to be multifunctional and general, MCUs are highly optimized in terms of firmwares and code and the hardware. So when it comes to optimizing the hardware, it can be very constrained and selective about the firmware resources they have is just for that dedicated task. So it's very resource constrained. And that's also why it's kind of very cheap, and which makes it very widely deployed in the real world scenarios, like factory machines, IoT devices, whatever you name it. But eventually, they're just single chip computers, which has all the components that a computer may have. So it's kind of unsurprising that the security situation with those devices are not so good. The attacks on them are on the rise, and there's numerous reports about how bad, how unsafe those devices are. And so now we ask the question, why securing or finding bugs in those devices are so difficult? So probably you will have a pretty good understanding when you look at the address space or memory layouts of the MCU. So take Cortex-M or ARM Cortex-M, for example. You have designated spaces for code, which is usually flash, and you have SRAMs, which is dynamic memory, and you have peripherals here. And the first difficulty with them is that it's kind of very resource constrained, like I mentioned earlier. So even if you have this huge segment dedicated for those memories, in reality, you only have a very small chunk of memories available. Like in Flash, you just tops 1 to 2 megabytes, and in RAM, it's usually even smaller. And the second thing is talking about the peripherals. Those tiny little devices have a lot of peripherals. We're talking about USBs, USARTs, GPIO, or timers. Those peripherals map their registers into this address layout using memory map IOs so that the processors can access their registers and interact with those peripherals. And those peripherals are kind of a lot, and even for one devices. But if you're looking at different vendors, they have different implementations. That makes the problem even harder. And another thing is those peripherals, they are proprietary and they are protected. You don't know what's really going on under them. So that's the two main things that's so difficult with analyzing those firmwares in deeply embedded devices. And the current wisdom to apply dynamic analysis, so in our case, concurrent execution for them, is that all of the work, all rehost them, almost all of the work, rehost them. So what's rehosting? So let's say we have a device. It has the hardware that we just talked about, and it has the firmware, which is designed to do whatever it is designed to do. And we want to run some dynamic analysis on them, let's say concurrent executors. So for our case, it's concurrent executor. So it's kind of expensive. And one thing you need to understand about concurrent executor is that, so one simple component, like say the solvers, the symbolic solvers for the concurrent executor is like 700 megabytes, but you only have 1 megabyte of flash, so it's never going to run. So what does the current work do? So first of all, the first thing is hardware in the loop. So it works something like this. You still have the device and you have the firmware, and you have to run the concurrent executor somewhere, so they run it in the PC. And what they did is they use the emulators to host those firmwares, because emulators have a reasonably good emulation for different architectures of CPUs, and that's where you can run firmwares. But when it comes to access to the peripherals, they don't have a so good emulation for them. So what they do is they ask the real device to perform those accesses for them. So through GDBs, and they communicate hardware events. So there are a few things kind of bad with them. So first of all, it's kind of expensive. You can only, for some, in early stages, you can only, oh, sorry, we have a pop-up of Windows. So yeah, so for the whole communication is kind of expensive. So as a result, as low as 5 hardware accesses can be performed per second, which is not good. And it's hard to access all the hardware components on the MCUs, for example, DMA, is still kind of challenging at this moment. And when you do this communication, you have to hold the CPUs on the device, which breaks the real-time operation that's commonly relied on by those firmwares. And you need GDB. And for sometimes, the GDB interface is very pricey, even $3,000. And we don't really want that. And the second thing is, and it's kind of popular in recent years, is emulation. So instead of forwarding those hardware accesses, you use modeled hardwares with very simple heuristics. But in reality, those peripherals are kind of complex and proprietary. And if you use simple heuristics to replace them, you have a lot of false interactions, which leads to a lot of false positives, which is also not good. So what are we looking at right now? So I think the objective for a better Concolic execution is that we want high quality peripheral accesses, and we want them to be fast. And we don't really want expensive interfaces. We want the framework to be universally applicable, and we want to support all the peripherals. And I think essentially we're looking at something like this. We ask the firmware to tell us whatever we need to know in order to perform Concolic execution. And that's basically what we do, or the basic idea of what we do in this work. So there has a lot of benefits. For example, you don't really need to know all the nitty-gritty of the hardware accesses anymore. You just ask the firmware to tell whatever you need to know. There's no emulators anymore, and you only need a very basic serial port. Which means that you don't talk GDB. We design a protocol to replace GDB, and there's no CPU halting, which is good. And you support all the hardware peripherals because they are all run inside the device. So the idea of this is kind of, how can we do this? It's kind of simple. So let's say at compile time, the idea is at compile time, you have a reasonable understanding of what's going on inside the firmwares. So let's say you are reading one integer from the memory. So at a compile time, you already know it's reading. And you also already know it's reading 4 bytes. What you don't know when you try to build a symbolic constraint is that you don't know the address to the RAM that you're reading. So that's why we record this symbolic constraints in this form at the compile time, and we just ask the firmware to report whatever is necessary. So this holds, as you can see here. Once we know those holes, we can build the symbolic constraints, and we can solve the symbolic constraints. So the workflow looks something like this. So let's say you have an x86 PC, which is normal, and you have the firmware source code. So you use LLVM, to compile and instrument the firmware, which gives you the for example, for our case, is Cortex-M firmware, because like LLVM, thanks to its modularity, it supports a wide range of architectures. So our framework is also applicable to all those different architectures. But for our case, we primarily focus on ARM Cortex-M because it's popular. And at the same time, it also has the unfilled graph, which is something which is exactly looks like here. We are waiting to build the symbolic constraints. We just don't know certain informations, and we are asking the firmware to tell us that. And we embed those information in the unfilled graph. And in online testing, we flash the instrumented firmware onto the device, and we connect them through a very simple serial port. And we just fill the unfilled graph, and we call to the Concolic executor to build and solve the constraints for us. So now we have Concolic execution. We can actually do something a little bit more cooler, which is hybrid fuzzing. So let's say we have a Concolic executor. So in our case, it's SymCC. It has APIs to build and solve symbolic constraints. And that's with the help of unfilled graph, which calls to the APIs of SymCC and builds and solves symbolic constraints. And what it does is it connects to the MCU through a very simple serial port. And at runtime, this firmware will tell you whatever you need to know, so you can proactively build and solve symbolic constraints. And at the same time, you can also exchange the inputs with FL. And that's basic a functional hybrid fuzzing for you. And this from Shift that is presented like 1 hour or 2 hours ago in this conference. And what it does, Shift handles the ASAN and code coverages for those MCUs, and so that the PC, the AFL has a reasonable understanding of what code has been executed, and if there is a memory violation that is triggered by ASAN, it also knows that. And then the input exchange is carried out in the workstation. And this is to the best of our knowledge, this should be the first practical hybrid fuzzing for deeply embedded systems. Yeah, we call this SHACO. I think the name is kind of smart. Anyway, so in terms of evaluation, we compare with the state-of-the-art Concolic executor with SimCC to our knowledge, and we are even a little bit faster than that because we parallelize concrete execution and symbolic execution. And of course, we are 1,000 times faster than Avatar, which is the classic hardware-in-the-loop design that we just showed before. And in terms of, we also evaluate code coverages. We run for 24 hours, and we keep looping the newly generated inputs back to the system, and we evaluate the accumulated cover edges, and we are better than both of them. And in terms of overhead, so overhead is kind of important because you are building a new firmware, and you flash that on the MCU, so you don't want them to be you want them to be fit into those tiny little devices. So it's workable because we instrument some new code, so the flash overhead is kind of like 27%. But in terms of RAM, we make some optimization, so it's only 2.9%. So I think that's a very reasonable overhead, and it's universally applicable to all the MCUs that we have experimented with. Also, we compare with the bug detectors, the pretty popular theme of research for the past few years, especially PIM and fuzzware, to test to see if we can help them prune the false positive because we use the real hardware. And it turns out we, in terms of detecting all the known bugs, so as you can see here, this is the true positive. We detect all the known bugs within a reasonably small amount of time and without any false positives because we use the real hardware. And if you look at those emulation-based approaches, they suffer from not supported MCUs or not supported hardware features that makes the booting process failed. And so we also have a demo to show you guys like how fast this system is. So on the left side of the screen, we run SimCC repeatedly, and on the right side of the screen, as you can see that we talk with a serial port, and this is the CO3 our work, and we can like they're trying to execute the same program, but this is executing in the PC, and this is executing with MCU, and now we execute SimCC and keep looping, and it's like performing Concolic execution, and it's kind of like this. And we at the same time we are running our work, and which is kind of fast. So not so fast, but it's kind of fast. So right, yeah. Now thanks so much. So all the code are available, and feel free to play with it. So we so we are not able to get the third batch because we have to get MCU to the hands of the reviewer, but it's single blind, so we just don't bother. And we also support a CC program, so which means that you can carry out the whole process that we just described in the pure PC environment, but not through serial port. We use USENIX domain sockets for that case. So yeah, I think that's pretty much all. Thank you so much for listening, and I'm happy to take questions.